Hello everyone, today we'll talk about the problem replace words. There is a story given about root words and derivatives. If you want to read it, then feel free to do so. And essentially the problem is that we're given a dictionary of words and also a sentence which consists of words. And we want to, whenever some word in the sentence has as a prefix a word from our dictionary, then you want to replace that longer word with the prefix from our dictionary. And if there are many ways to do so, we have to choose the shortest prefix. For example, if we have the word help in our dictionary and we're given the word helpful in the sentence, then we can replace that word helpful with just the prefix help. Now in general, when we have problems where the process that we have to do is very simple, there isn't much algorithmic depth within it, and especially when we work on some prefixes, then typically that problem can be solved using a tree. That's tree written as like the middle of the word retrieval. This is a very simple structure. I think one of the simplest possible data structures that exists when it comes to just wrapping your mind around it. Because its idea is very simple and very natural, and utilization of it, the way you can use it to solve problems, is also very natural and easy. So here's an introduction. A tree is a compact way of representing a set of words, a dictionary of words. So for instance, if you have words like car and cat and dog, then we can represent it, for instance, as a list of words. But one way to represent it is to have a tree starting at a root. That root would be the empty string. And now we can, for every letter that can be the first letter of a word, have a child corresponding to that letter. And so in this representation, you can, I think you can immediately see how this tree represents exactly the set of our words. Because I have here marked with a dot when the word ends, and we can go down the tree and up to some node with a dot, and that is one word in our dictionary. So CAR is one word, CAT is another word, DOG is another word. And you also saw how I created it, how we can insert words into the tree. So for instance, if now we have a word CB, then C already exists, we go to a B, and that's final. If we also now add do as a word, D exists, O exists, and now we only mark it here with a dot because that word also exists. So for instance, if we go here, DOG, we see that both dog exists and also this do word also exists because both have dots. So this is a very simple structure, it's very easy to create it, and it's very easy to use it to solve problems like this, because here, if we want to know what is the shortest prefix in our dictionary for a given word, we just have to traverse the tree built for our dictionary along the path dictated by word. The first time we see a dot, that is the shortest prefix. And if we never see a dot, or perhaps we find out, for instance, that here the question is for, let's say, C, A, B, then we go C, we go A, and there is no child for B, so we know that there is no prefix in our dictionary corresponding to the word CAB. So it's extremely simple, and the rest is just implementation. In general, you might want to have a template ready to just copy-paste, but one way you can implement a tree is just to, for each node, have both the information if that node is final, which is the dot on the diagram, and also a dictionary from a letter to every, so from every letter to the child corresponding to that letter. Here it will be a default dict that will just create a node when we ask for a given child. We remember the root, which is this node corresponding to the empty substring. By inserting, we just go through start at root, go through all the letters, and go to the children. So here, because we implicitly create the children when we go down the path, we just can write it like this. Even if the children do not exist, then they will be created. And also we have to remember to mark with a dot that this is a new word that we have added. So for instance, If we call it on CB, then we go down to C, creating it if it's necessary, down to B, creating if necessary, and then this is the final marker at that node corresponding to CB. And now how do we find the shortest prefix? Well, we start at root, we go through all the letters in the word. If now we are at a final node, then this is the shortest prefix. If we cannot go down in our tree, that means there is no prefix, since we haven't found it already and there is nothing down, no words that have a prefix as long or longer exist in our dictionary, so we just break out of the loop. Otherwise, we go down the corresponding letter. And if we found nothing, then we just return the length of the whole word. And in that case, if you have tree already written, the solution is extremely simple. You create the tree, you insert all the words in the dictionary, and now you just take the prefix corresponding to the length of the shortest prefix from your tree, and that is the answer that you just join with spaces.